Hello everyone, thank you for watching that talk about the impact of the climate change on astronomical sites, observing sites. So my name is Faustine Cantalloube and I'm working in the south of France. And my main area of research is high contrast imaging for exoplanets and circumstellar disks from ground-based telescopes. So by studying the link between the performance that we have and the interaction with the atmosphere, I naturally came to study how climate change does impact our ability to observe from ground, obviously. So the image in the background is the first image of Earth, according to Wikipedia, made in October 46, and just represents our view of our planet, which I think quite mesmerizing, just to say. So what defines a good astronomical site? So we can think of many aspects, but maybe the main ones would be the latitude, of course, because you want to access numerous targets. For instance, the center of the Milky Way, which is called crowded, and the Magellanic Clouds. The second aspect is you want to have clear and stable weather, to have as much observation time as possible, as available. The sky transparency is super important, so you want to be far away from cities to not have light pollution and also low humidity and so on. And the last one is accessibility. For instance, Antarctica would have been an amazing site, but it's unfortunately very hard to access it. I mean, there are still telescopes there, but that's also a key point. If you want to have an observatory that is prolific, to have access to that place. Hence the picture of the road here that leads to Cerro in Chile. So the parameters that we can use to assess the observing site quality are numerous, but they're mainly the cloud coverage, of course, the humidity, the water vapor, because humidity, water is going to absorb a lot of wavelengths. So if we want to do precise spectroscopy, we need to really have a dry environment as much as possible. Mainly the sub-millimeter. So here I'm really focusing on the visible infrared, but you can do the same with sub-millimeter radio, and the main impact would be water vapor content in the atmosphere. The third one is atmospheric turbulence, and a last one that is not directly linked, but it's interesting to study is the temperature. So all of those parameters have to be taken in the framework of the climate change. So you see here on the right, the famous Killing curve, showing the increase of atmospheric CO2 concentration with time, which almost increased by 50% compared to pre-industrial era in the 18th. So climate trends is those weather conditions that average over more than 30 years. So those 30 years is a convention in climatology, but it really makes sense because the climate system on Earth, there's a lot of cycles, and those cycles have periods of about a few years to decades. So if you want to average those cycles, such as the one you might know, El Niño Southern Oscillation, you really need at least 30 years so that what you're claiming makes sense in terms of like global trends. So what do we have for analysis? So first off, because of this 30-year timescale, we finally can use the observatory weather database because, for instance, the Paranal observatory I've been focusing on has been built in the 90s. So we do have data now that are like 30 years of data. So we can start really using those data and do climate trends. The second aspect is the in-situ data, such as balloons, but also data from airports or satellites, whatever is available. So balloons, for instance, the Antofagasta city, that is the closest to Cerro Paranal, sends 2 balloons a day to make an atmospheric profile. An important tool is the so-called reanalysis data. So in Europe, USA, Japan, and other places, weather centers are actually gathering all of the data that are available, so airport satellites, balloons, and they're really trying to pave the whole globe with those parameters. So not only in altitude, but also in space and also in time with different resolution for each of those parameters. So you can have, I don't know, monthly average, but also hourly average at different pressure level in some location, thanks to this reanalysis data, and everything is accessible. A last one is the climate projection data. So that's also accessible through the IPCC. For instance, the IPCC projects of intercomparison, the CMIP project. And that's taken from pre-industrial era to about 2100, so a century from now. And with that, there are many institutes that are providing their data, and you can like find the spot where you want to find these projections. But one very important thing is that I'm obviously an astrophysicist, I'm not a climatologist. I'm a physicist, so I can understand hopefully and know if it's well explained. But I really need to cross-check and to know how to deal with those data, thanks to climatologist collaborators. So I've been always cross-checking with them. So one third thing that we can look at, for instance, is the SING. As you know, the SING is very important for astronomy sites. So the better SING, the more angular resolution you can have when you're doing imaging, and the worse the blurry is the worse SING, you have blurry images. So we did have a look at the SING, but you can see on this blue curve that it's kind of increasing. But there are two things: is that many things happened since the 80s on that site. So the mountain's been shoveled, and of course the UTs, the unit telescopes, been built one after the other. So it might have impacted locally this stream of air, or indeed it might be due to the climate change. But actually, when looking at the IPCC reports, but also another study made up by a collaborator called Caroline Aschelbacher, the ground layer wind seems to not be changing. And also another collaborator at ESO, colleague at ESO, has been monitoring if you could spot directly in the images a change of quality, and they didn't see anything significant. So we don't know yet, but there's high chances that it's actually just a local effect due to the building of the telescopes. When we talk about atmospheric turbulence, so here we've been thinking about really the ground layer, but there's also a very important role played by the high wind speed layers, and particularly what we call the jet stream. So it turns out that Cerro Paranal, the observatory, is really below the southern subtropical jet stream. So the jet stream is a very thin layer of air, of wind that goes really fast. It's at 12 kilometers in altitude, and it's very thin, and it can go to about 60 meters per second winds. And so what you can see here in that image is a high contrast image with which I'm working. And this huge bright flare in the middle is actually the light of the star that is leaking along the direction of the jet stream wind. So the jet stream is direction is represented by this black arrow here. So it's really annoying, because if you have that, you can't see the planets that are lying close to the star, obviously. And we observed a slight increase, but on the average, and that's not exactly what we want to look. We want to look at how many times it happens, that is a fast wind speed, how long does it last, and if the frequency of those events increase. So this has to be refined, but according to IPCC report and some other research, what we know is that the jet stream might shift polarwards, so go even southern. So now it will go even better on the Paranal observatory, because now it's just like slightly touching the south of the jet stream, but now it's going to go even forward. And also the increased oscillation in speed, so the stability of the jet stream might be shattered by climate change. Very briefly, the humidity. So we had a look at the particulate water vapor, but it's very low at Paranal. So the median particulate water vapor is 2.5 millimeters. Which makes the Atacama Desert the second driest place in the world after Antarctica. So you need very specific sensors that can work under low humidity environment. And we have those only since 5-6 years now. So we cannot make any trend, but we can look at the projection scenario again. And again, in the worst case scenario, we could observe a slight increase. But this is also talking with climatologists. Turns out that it's very difficult, the humidity, to deal with and to understand how things work. And that's not, we know the global scale that we know, but like on small places, like just localized on Paranal Observatory, that's very difficult to downscale our projections to that place and take into account the relief, the orography, and all of those parameters. So there are tons of things that we still could do with that kind of study. So as I said just now, we find the humidity for this very specific place here that is on the coastline with the Andes and a very extremely dry environment. So some climatologists are actually specialized on that, experts, and they're doing some experiments there. But there's also the laser guide stars. So it turns out that if they climate change is human induced, as you all know, and it's one of the proof of that, the scientific proof, there are many of them, is that the troposphere will warm up, so it's gonna dilate, like getting bigger, and the stratosphere is gonna shrink. And the climatologists for a long time, they've been using kind of laser guide stars to monitor the tropopause, so this place where it goes up and down. And so we could also use laser guide star data to monitor that. And actually it's been made. So there is a few papers about that. That's very interesting. So I should at some point maybe would like to do a bibliography to give some results. And also the particles, the aerosols, particulates emitted by, for instance, the mining industries, copper mining industry mainly surrounding the Paranal observatory. Those can scatter light and make that the sky is brighter. So it can have an effect also on the clouds coverage because those are kernels for condensation. So it can create more clouds on top of the scattering of the light. More simple than that, we've been looking at the temperature. So we observed that the temperature has been increasing by 1.5 degrees. It's consistent with the analysis data, and the projection, the worst case scenario is plus 4 degrees Celsius. So there's a few side effects about that, but I'm not going to go into details, just to show that with the data, we actually do see the impact of climate change straight with the observatory data. But one important thing about the increase of temperature is that we know that the frequency, the intensity, the duration, the surface damage, and the risk time range is increasing. The risk time range, that the periods of risk of forest fires and bushfires is increasing. And that has a lot of consequences. So as you probably know, Mount Stromlo was destroyed in 2003. The Mount Graham was threatened many times and more. And more recently, the Mount Wilson in 2020, but also 2021 was awful last summer, and many observatories were like threatened by the flames from huge fires. So that's a direct consequence of the increase of temperature. This also has a consequence on the quality of the sky, because if you look at the plume, the smoke plume, for instance, here from the Dixie Fire in 2021, so that's from NASA satellite imaging. So you see here, so this is California on the left, and so in North America. And here, this is the analysis data of the particulates. So I chose the PM 2.5, so 2.5 microns particles. That are very dangerous for health because they're very small, so they go very deep into the lungs, and you can see that it kind of correlates with that plume of smoke that we observe here. And the International Dark Association recently gave a study from people working in national parks in Utah, so national reserves, and they use this quality sky meter. And 1,000 kilometers from the forest fire in 2010, they realized that the sky background had increased by 3 magnitudes. So they went from gorgeous sky to like too bright sky. And at the same time, they monitored that the air quality in terms of 2.5 particles increased by 10. So there is a correlation, and that's also another thing that we can think of. Those forest fires will also degrade the clearness of our sky. So to go further, because when I started thinking about that, of course, first I wanted to have numbers, I wanted to have data, I wanted to, do like the same as I'm doing with my work, my astrophysics work, but with climate. But then I realized that that's not what's going to happen. I think what's going to happen, so of course, just an overview, so we'll be touched by light pollution that is from the ground that is increasing, but also the light pollution that comes nowadays from the constellations of satellites at 400 kilometers altitude. But the most important is that those big telescopes, those big projects such as extremely large telescopes on even scale, they need a lot of energy. And this energy resource that we need is something that's going to be impacted, as we know, by climate change socially. Same, we will have to need access to resources. So here, that's one of the trucks that brings 20,000 liters of fresh water twice a day, at least, to the Paranal Observatory, for the observatory to work, for people to drink water. And it's a very dry environment, so you don't need water. So we do need access to resources. And that's the thing we know it's going to be extremely affected by climate change, as said by the Working Group 3 of the IPCC. And another thing is the IPCC reports also states that social stability might be really impacted. So for instance, here you see the picture of the riots in Chile, the protests that have been just before, like in 2020, just before the COVID outbreak. And during those days, astronomers and operators, they couldn't access to the telescope because everything was, locked down. So it clearly affected directly how it works. And so a very last thing maybe is like to talk about like when we come to a desert place and we build those observatories, this hotel, this restaurant, it does affect the ecosystems around. Actually, we have a few examples of how like the animals around and were affected by just the presence of humans and the presence of food stocks and everything. So in a way, like climate crisis is gonna affect mainly those aspects. Mainly access to energy resources and social stability is extremely important actually for the good operation of telescopes. So I just would like to finish on that picture, which is a picture taken by Alexander Pollack from the SETI Observatory, the Search for Extraterrestrial Intelligence. That was in 2021 during the fire. So you can see this huge smoke from the gigantic forest fires that happened last summer. And the sun through that is very red, as I said, like it's absorbing the light. And I found that very paradoxical because we are looking for extraterrestrial intelligence. We are looking for inhabited worlds. We talk a lot about habitability of exoplanets and things. And at the same time, the uninhabitability of our own planet is being threatened. So that's why I put that picture here to raise this question of that this is really weird that we came to a point that we're so close to it and yet we're destroying our own. And the other things that we're always going to very isolated places to study a habitability of other planets. And I also found that interesting thoughts. So thank you very much for listening to you. I'd be happy to have any questions via Slack, or don't hesitate to send me an email to give me feedback, give me new ideas. I'm just doing kind of bibliography, and I hope that I gave you the keys to think a bit more about those aspects. Thank you very much.